So today, yes, 10 minutes to cover Antarctica. Antarctica is a vast place, and to me it's a very beautiful place. It's also a very special place, and hopefully in the 10 minutes I've got, I'll convince you it's a very important place. So you might be wondering where the title comes from, an awful place. Well, it comes from Captain Scott, and he wrote these words in his diary on arriving at the South Pole. He didn't find the sort of blank white canvas that he'd hoped for. There was somebody else's flag there in the way, and so he was understandably despondent, I can imagine. So this probably coloured his judgment and influenced his choice of words. But the reason that I wanted to sort of use this quote, and particularly this image, was actually nothing about sort of romanticising the so-called heroic era of Antarctic sort of exploration, but really just to highlight the time frame on which all this work has been done. So this is Scott on the Beardmore Glacier in December 1911, and they were on their way up to the polar plateau, on their way to the South Pole. Now we were working on the Beardmore Glacier 99 years to the month, pretty much actually on the day we were there over Christmas that year, 99 years after they'd been up there. So that for me really kind of puts some sort of temporal bounds on the work that we do. It's only 100 years pretty much of Antarctic research. It's not a long time. And in fact, when you think that actually following that heroic era, we then had about 40 years of two world wars, Great Depression, various other things going on. The world's focus was definitely elsewhere. So not much happened in Antarctica until 1957, the International Geophysical Year, 1957-58. And that was when many of the bases were first founded and when sort of scientific research was really kick-started. So in that context, then pretty much everything that we know in terms of the science around Antarctica has been gleaned in the last sort of 6.5 decades or so. So it's not a particularly long window. And of course, in those days, in fact, even following the geophysical year, the people that were going there to do work were just going to individual sites because that was all that was possible. There were a few planes flying into certain areas and people would lean out and take photos of the ground and so on. But it's really only since the advent of Earth orbiting satellites that we've got a clear picture of the entire continent. And that's really only been since 1979. Now what we're seeing here is just the last couple of decades. This is a visualization from NASA, and it's showing you these bright colours in certain parts of the Antarctic continent. And those are the areas where ice is being lost most quickly, so where the ice is melting most quickly. Now, as we look at that, we can see that there's a very handy graph on the left-hand side showing a downward trend, which is not good news from an ice sheet perspective, because it means that more and more of the ice is getting lost to the ocean. It's melting because of warm ocean water, and that ice is then flowing into the sea more quickly. And that, of course, leads to a rise in sea level around the world. So this is really the way that we look at the whole of Antarctica now, which previously wasn't really possible. Now, the work that I do isn't so much around using satellite information, but it's about using computer models. So I run computer simulations where I try and understand how the ice sheet might continue to change if that warm water continues to attack the ice sheet. So what you're seeing here on the left-hand side is a number of climate stripes, if you like, the vertical stripes. And basically everything to the left of where it says now was kind of colder than present. So that's just a sort of a normalized temperature. And these ribbons in the middle there show us what could transpire in the future. So these are pathways that we could follow depending on what we do with greenhouse gas emissions. So methane, carbon dioxide, nitrous oxide, things like this. Now, we have a number of different pathways. I'm going to use this fancy, there we go. Yeah, it's cool, eh? So if we follow this, this upper pathway, this is a pathway in which we carry on emitting large amounts of carbon dioxide, lots of different greenhouse gases, without any real regulation. And we carry on doing that, and the temperatures reach 8.8 degrees. So, I mean, let's say notionally somewhere between 8 and 10 degrees in the next few centuries. That's pretty alarming. And what we can see is that in that scenario, the ice sheet, hopefully you can make out here just where the cursor is, what used to be an ice sheet, the West Antarctic ice sheet, that part of the ice sheet was about 3 kilometers thick. It's now gone, it's now open ocean. So all that ice has now gone into the sea. And that means that the sea level around the world has gone up by somewhere between 5, maybe 6, 7, 8, even 10 meters. That's pretty alarming. The other alternative is that we follow a pathway down here where we strongly, aggressively mitigate emissions, and we follow a path where temperatures, they may go up a little bit over the next, or over the current century, but they come back down, and we stabilize below about 2 degrees, which is the Paris Agreement climate sort of limit, if you like. And in that scenario, we end up with an ice sheet that even in a few centuries, maybe even a few millennia, still looks like the one that we know today. So these are computer simulations, and this is what I try and refine over the years that I do this work. And the impacts of losing a lot versus a little are quite manifest in terms of what we feel in New Zealand. So we don't have to wait thousands of years to feel the water lapping around our feet. Even a 10 centimetre rise in sea level means that we get a flood, an increase in the flood frequency, nuisance flooding around the coast of about 3 times. So you compound that each time, and with 30 centimetres of sea level rise, it doesn't sound like much, but all of a sudden your 1 in 100 year flood at the coast becomes once every 3 or 4 years. Now you've just got to think of the social disruption that causes and the economic impacts that would manifest. So it's definitely a very real concern, and it's not something that's just going to happen in 100 or 200 or 1,000 years. It has other impacts as well. When we put all that cold fresh water into the oceans, it cools obviously certain parts of the ocean, and it stops the ocean behaving the way it wants to, basically. And that means that the ocean doesn't transport heat the way it used to. So some areas get much warmer because the heat is blocked. In other areas, the globe gets colder. So what this means is that over coming decades, not just the climate will change, but the weather within that climate change will also be altered. And we'll see much greater variability from one year to the next, season to season, year to year, decade to decade. And that's something that, again, is going to be very disruptive. You think about the economic impact of unpredictable seasons when we're talking about food security and being able to feed our growing population. So these are very real impacts, and they're already starting. So these are just a couple of the main sort of impacts from a changing climate and a changing Antarctica. And it was these impacts, as well as many others, that led the Secretary General of the UN, Antonio Guterres, to say that this report, the climate change report from 2021, the Intergovernmental Panel on Climate Change Physical Science Basis, was code red for humanity. He was basically saying, it is time that we do something about it. It's not a problem for future. This is the time where we need to act. And there's some statements there from the report basically saying it is virtually certain we're going to lose ice, virtually certain sea level will continue to rise. We have confidence that we will continue to lose ice and sea levels will go up. So that's a challenge for us as a community. The way we're trying to meet that challenge, over the last few years in the Antarctic Research Centre, we've built a cohort of early career researchers. And we're trying to train those researchers in all aspects of Antarctic and Southern Ocean numerical modelling. So we have many other people doing different things, but this particular group are all focused on climate modelling, atmosphere, ocean, ice sheets, sea ice, many different components. They all interrelate. And of course, ecology is part of that as well. So this is the way that we're trying to contribute to it, to solving these problems. It's not everything. It's a small group, but we are growing. We've grown a lot over the last few years. We're now in a position where those new postdocs that we recruited are now recruiting their own PhD students. We're beginning to get this sort of longevity. So by all means, jump onto the website, find out more about us, sign up for our newsletter if you like. That's where we're at with our work. It's a work that obviously takes a vast team. I couldn't be here without that team. I think that's true of all of us. So I want to acknowledge everyone that I work with. I can't possibly list everybody on this slide, but of course, huge thanks to the Royal Society, goes without saying, to the university that's supported me for the last 15 years and always been very supportive of the work that we've tried to do. People like Tim Naish, Lionel Carter, Tim Stern, Alan Mix, the people that have actually made this nomination happen, and of course many, many colleagues. So thank you very much for your attention. I'll leave it there.
Thank you. We have a few minutes for questions, and Trolls has the microphone, so when you get the microphone, please hold it up and ask a question for the people. It's being recorded. That's why you need the microphone.
Well, once again, is this on? No, it's not.
Steve, it's on, isn't it? You can't hear it, but it goes into the record.
Sure.
Let's just go with it. Trust them.
Hold it close.
Once again, congratulations. A quick question, because I know I can't see if there's others, but no doubt everyone had their hand up. One of the things that's always interesting is whether some of this loss of ice shelf is a linear process or whether some of things going to go kapoosh suddenly, and no matter what happens after that, it doesn't matter. So in your sort of long line scenarios, what are we on some inevitable track where we're all doomed?
Yes. No, you raise a very, very good point. Nonlinearity is our enemy, essentially. And one of the things that we do with the models is trying to understand where those nonlinearities exist. Okay, so we're looking with the models to say, well, if we do this amount of incremental forcing, will we get an incremental change in the system? And the things that worry us is when we put in an incremental forcing, but we get an exponential response. We see a change which is disproportionately large. So that's a key concern. That's where models are very, very useful. And we lean a lot on the geological record as well, going back to the deep time record, the sediments, the rocks that can tell us actually there was a small amount of warming, but boom, the whole ice sheet was gone. So that is a key part of what we do, trying to train the models on the geological data.
Maybe it follows on a little bit from David's point there. Are you guys modelling the Thwaites Glacier, the so-called Doomsday Glacier? I could see it on the map there. It looks horrible.
We generally run whole continent ice sheet models. So we're implicitly modelling that glacier. Yeah, and we just had a paper out. One of my former PhD students, who's now a postdoc in our modelling group, just published quite a high-profile paper on that glacier, which got some traction. We had a conversation article and so on. So yeah, the world is watching that glacier, and it's something we'd like to understand more.
We have time for one more.
Yeah. I mean, you kind of answered it, but you didn't quite answer the tipping point question. So there is the non-linearity, but is there a tipping point?
Yes. Don't ask me where. So the devil is in the detail, right? We know that there are non-linearities in the response, particularly in certain sectors of the ice sheet. Quite often we look at the ice sheet as a whole, and then it's quite hard to say that there's a tipping point because different sectors, different drainage basins behave in slightly different ways. And that then when you aggregate them, it kind of smooths out those tipping points. But when we look at an individual glacier or a single drainage basin like the Thwaites, the Amundsen Sea sector, we can say that under a certain amount of warming, we get kind of fairly small amount of response. But then there might be a certain sort of window between maybe 1/4 of a degree of ocean warming and 1/2 a degree, where all of a sudden we lose West Antarctica, if it plays out for hundreds, maybe a couple of thousand years. So we know that there's a tipping point there. The challenge for us as a community is really nailing that down, because different models will say slightly different things. But again, that's where we lean on the geological evidence and say, well, actually, that sort of window is about right based on what we know from the rock record.